Now, in this particular class, we will start the simplex method, that is solution of linear programming problem by simplex method. Let us see, we are having z, which is a linear function, because as you know LPP, the objective function as well as the constants are linear. It is a linear function of n variables, say x1, x2 and xn. We are writing z equals c1 x1 plus c2 x2 like this way plus c2 xn, cn xn, say this is 1, subject to, I am just again repeating, I have written earlier a11 x1 plus a12 x2 plus a1n xn, this is equals b1, a21 x1 plus a22 x2 plus a2n xn, this is equals b2, like this way a m1 x1 plus a m2 x2 plus a mn xn equals bm. This we are denoting as number 2 and xj greater than equals 0, where j takes the values from 1 to n. So, this is number 3. So, the general LPP can be defined as maximum optimization, that is maximization or minimization of a function z equals c1 c2, c1 x1 plus c2 x2 plus cn xn defined here by 1, subject to satisfying the constant 2 and 3. Whenever you are trying to satisfy the constant 3, basically denotes that it is a non-negativity constant of the decision variable. So, any n tuple solutions x1, x2, xn which satisfies the constant 3, we call it as the solution, this is a non-negativity. Now, you take n tuples x1, x2, xn, a set of n tuples x1, x2, xn, this satisfies the constant 2, then you will obtain a solution of the LPP. Please note this one is, if I obtain a set of tuples n tuples x1, x2, xn which satisfies the constant or condition 2, then it is a solution of the LPP. Now, any solution which also satisfies, if a solution satisfies the non-negativity condition 3, then we call it as a feasible solution. So, you are getting solution, then you are having the feasible solution. Now, whenever you are having a feasible solution, if this feasible solution optimizes the objective function z, then we call it as the optimal solution. So, please note this one, that whenever a feasible solution optimizes the objective function z, then it is an optimal solution, and if the solution which you are getting, that is, if I have a feasible solution and if this solution is basic, then we call it as BFS or basic feasible solution. So, please note this one, I am re-emphasize these things, because afterwards very frequently we will use these terms. You have a problem, that is, you have to either maximize or minimize a function z given by equation 1, subject to satisfying a set of constants given by 2 and 3. 3 denotes the non-negativity constant of the decision variables. Now, a set of n tuples x1, x2, xn which satisfies the condition 2, then we call it as a solution. Whenever the solution satisfies the non-negativity constant 3, we call it as a feasible solution. If the feasible solution is basic, then we call it as a basic feasible solution, and if the feasible solution optimizes the objective function z, then we call it as a optimal solution. Now, let us see what is the solution of LPP by simplex method. What are the steps? What are the steps used in this particular method? The steps are: first, compute the trial basic feasible solution. Now, as I have told, you have the feasible region, you have to find out the basic feasible solution. We have defined earlier what is basic feasible solution, what is basic solution, and from the basic solution how to find out the basic feasible solution. Here we will use the concept of linearly independent vectors. Whenever we are going through the examples, we will discuss it. So, first is the compute trial BFS. Number 2 is test the initial basic feasible solution for optimality, that is whether the basic feasible solution is optimal or not. How to test whether it is optimal or not, that is we will see after some time. Then number 3, improve the initial basic feasible solution by a set of rules, that is you have the initial basic feasible solution. If the solution is not optimal, in that case I have to improve it by certain rules or techniques, and I have to repeat the step 2 and step 3 until I derive to the optimal solution or I terminate that there is no solution. So, these are the basic 4 steps. Please note this one, that I have to first find out the trial or initial basic feasible solution. I have to test whether this initial basic feasible solution produces the optimum value of the objective function or not. If it is not producing the optimal value of the objective function, in that case I have to improve it by certain rules, and then I have to repeat the step 2 and 3 until optimal solution is derived. Now, whenever I have a problem in simplex method, the problem we represent in tabular form, each term of rows and columns. Each row is represented by one constant, we will show it. Each column is represented by one variable, and top row corresponds to the objective function. So, basically we are giving the input in terms of a table, where each row is represented, first row of the table is corresponds to the objective function, and subsequent rows corresponds to the constants, and each column is represented by one variable. Let us see how it is being represented. Suppose you have a function, I have to maximize z equals 60 x 1 plus 50 x 2 plus 0 into x 3 plus 0 into x 4. I will come to this, why I am writing this one. Subject to these constants, the constants always should be equality. So, we represent it in a tabular form like this, where we will discuss what is CB, B, XB, x1, x2, x3, x4, Cj. Your Cj is here in this particular case, your Cj is the coefficient of the cost functions, that is coefficient of cost function is in x1 is 60. So, here I will write down 60, coefficient of cost function with respect to variable x2 is 50. So, I am writing 50 here. Then x3 with respect to x3, the coefficient is 0, here it is 0, I am writing 0 here. With respect to x4, the coefficient here it is 0. So, I am writing over here. Now, from here what is which portion of this. If you see, this is a matrix which we can write down 1 2 1 0 3 2 0 and 1. So, if you see, these two always will form a linearly independent vector. So, I have to see where I am getting the unit matrix, and corresponding to this unit matrix, whatever decision variables are associated, those will be the here basic variables. So, basic variables are those corresponds to those that unit matrix which I am declaring in this constant set. So, for x b I will write down here x 3 and x 4. So, x b what it corresponds to? X b corresponds to the basic variables which is arising from the unit matrix in the constant. So, my aim is to form one unit matrix in the whole constant set A, and from there I am obtaining the basic values of these variables. What is B? As you know, your equation is of the form A x equals B, that is B is this value. So, I will write down 40 and 60. Here, as we have told, first row corresponds to the objective function, that is coefficients of the decision variables in the objective function, and subsequent rows corresponds to the coefficients in the constraints of the decision variables. So, your first constant is x 1 plus 2 x 2 plus x 3 into 0 x 4. So, coefficient of x 1 is 1, x 2 is 2, x 3 is 1 and x 4 is 0. So, you are writing this thing, and similarly your x 4 next row will represent the second constant. Here it is coefficients of x 1, x 2, x 3 and x 4 are 3, 2, 0 and 1. Your C b value is nothing but the value corresponds to the objective function here corresponding to x 3 and x 4, or in other sense the coefficients of x 3 and x 4 in the objective function is the value of C b. B value we may write, we may not write. This is actually a 3, a 4 to denote the variables. Now, what is your z value? Your zj minus cj, this represents the reduced cost, that is actual cost, zj is the total cost minus cj, cj is the cost of this one. So, in this case what will be this value? B into x 1, I am just writing for this one, B into x 1 plus B into, or in other sense if I have to write down 40 60 into 1 3, that is this corresponds to x 1 minus C j, that is C 1, here it is C 1 is 60. So, this one. So, or in other sense it is 40 minus 180 minus zj, this plus this into this plus this minus 60. So, we will obtain the value as minus 60. So, like this way, I have written wrongly here, totally I have written wrongly. This is C b into this B value minus C j. Your zj minus C j is this one, C b into B minus C j, that is 0 into 40, 0 into 40 minus 0 into 60 minus 60. So, that the value here it becomes minus 60. Similarly, for this case 0 into this value 2 plus 0 into this value 2 minus 50. So, it will be minus 50. Since both are 0 here, so it will be 0 and this will be 0. So, like this way, here I have to check where it is most negative. Why it is most negative, that I will come to the point whenever we are going through the theory of simplex method. So, maximum value is obtained over here. So, wherever maximum value is coming, we say that this will be the entering variable. Please note this one. This will be the entering variable wherever we are getting the maximum value of Zj minus Cj. So, we will get this one. Now, to calculate where is the which one with the outgoing. So, basically if you see, you had the decision variables x3 and x4 and you are getting for the reduced cost negative values. So, I have to continue, or this feasible solution it is not providing me the optimum value. So, to get the optimum value there will be one entering vector and there will be one outgoing vector. Entering vector will be that one corresponding to that column where Zj minus Cj value has most negative value. And similarly, now you calculate xbr minus yj. What xbr minus yj? This is basically b by xj value, this one. This is basically b by xj value. Xj may be 1, 2, 3, 4. So, here this is the entering variable. So, variable is x1. So, that is it will be 40 by 1 and it will be 60 by 3. So, the minimum value of these two is obtained here. Minimum value is obtained for this one. So, the outgoing, this we say as the outgoing vector. Please note that this is outgoing vector. So, you have one entering vector depending upon where the value of Zj minus Cj is most negative. Then you have to calculate the ratio xbr by yrj. Xbr by yrj is nothing but b by xj, and xj represents corresponding to the entering variable. For this case it is 40 by 1, it is 60 by 3, here it will be 40 by 1 and 60 by 3. So, outgoing variable is this vector will be x4 and incoming vector will be this one. So, these two meets means wherever if I draw a line, column corresponding to this is this, outgoing is this. So, they meet at a point 3 say. Here this we call as the pivot element, this we call as the pivot element, and this value we will see what to do. So, effectively what is happening for this particular case here, if you see now, whenever I am transforming my LPP in some form like this, from there I am putting it in a tabular form, I am calculating certain values of Zj minus Cj from here, then I am checking what will be the entering vector, what will be the outgoing vector, and basically I will repeat this process until my reduced cost Zj minus Cj is non-negative, that is greater than equals 0. This I will discuss what is the determining entering vector and outgoing vector also. Now, different forms are available, forms of LPP. Number 1 we call it as matrix form. In matrix form we will take the maximization problem, because always if I have a minimization by doing minus I can change it to maximization problem. So, maximize z equals C x subject to a x greater than equals or less than equals or equals b. I am writing the standard form and x greater than equals 0, where I am not writing what is A, B and C. A is the m cross n matrix, B is also column matrix 1 cross m, and C is a row matrix 1 cross n, and x is the n decision variables, that is the column matrix 1 to n. This we have told earlier. So, this is your one form, that is matrix form. From this matrix form we come to the second form, which we call as canonical form. So, whenever I am writing matrix form, then please write here minimum or maximum, then it will be all right, because your initial problem may be minimization problem or it may be maximization problem subject to a x greater than equals or less than equals or equals b and x is greater than equals 0. In canonical form, always we write the LPP in this form: maximize z equals C1 x1 plus C2 x2 plus Cn xn subject to a I1 x1 plus a I2 x2 like this way plus a In xn less than equals bi. I takes the values 1, 2 like this way n, and obviously x1, x2 and xn, all the decision variables are greater than equals 0. So, please note one thing obviously here, that we have changed now the form, whether it is maximization problem or minimization problem, I have to transfer it as a maximization problem. All the inequalities has to be only less than equals. So, whenever we will solve, we will always follow this notation. Problem will be maximization and the constants will be the minimization. So, suppose I have a function minimize z equals some function of f x. So, this problem I can transform it as maximize z equals maximization of minus f x. That is, if I make the negative of this, then automatically the minimization problem will be transformed into maximization. So, if my problem is minimization problem, in that case I will transform my problem into minimization by making the negative of the objective function. Now, I may have something like this a11 x1 plus a12 x2 like this way plus a1n xn, which is greater than equals say b1. So, in this case again this is greater than equals, but I have to change it into less than equals. So, what I will do, as we know the normal algebra, if I multiply both sides by negative sign, this greater than equals will be converted into less than equals. So, I will write down this like this: minus a1 x2 minus like this way minus a1 xn is less than equals minus b1. So, this is another type, and your constant may be something like this: a11 x1 plus a12 x2 plus a1n xn, this is equals b1, that is equality type, but we have told always we will take it as the less than equals. So, this equality I can write down, or in other sense I am writing in matrix notation. If I am having a x equals b, I can write down a x less than equals b, I can write down a x greater than equals b. Equality can be written like this: a x less than equals b and a x greater than equals b. Again, this is not acceptable here, because the constant always has to be less than equals only. So, this I will write down minus a x less than equals minus b. So, now both this constant and this constant are less than equality, the less than equals. So, therefore, if I have equality, first I will convert it into two inequalities of less than equals type and greater than equals type. Later, the greater than equals type will be converted into the less than equals type. One more thing can come here, that is, we always say x greater than equals 0 or x is non-negative, right. But if it is given that x j is unrestricted in sign, that is, we can't talk about the sign, it is not non-negative. It may be positive, it may be negative, anything. But in our canonical form, what we have told, always all the decision variables must be greater than equals 0. So, if this is the case, we can write down x j equals, I can represent it by two more decision variables, and I can write it x j equals x j dash minus x j double dash, where both x j dash and x j double dash both are greater than equals 0, where both x j dash and x j double dash greater than equals 0. This is required whenever we will work with dual simplex method. So, therefore, if x j is unrestricted in sign, then we write down x j equals x j star minus x j double star, and by this way we write down this one. This is the second form, that is canonical form, and the third form is which we call as standard LPP. That is, I have the original problem, from there I am transforming it into the canonical form, and from the canonical form I have to transform it into the standard form. My standard form will be maximize z equals c1 x1 plus c2 x2 like this way plus cn xn, subject to ai1 x1 plus ai2 x2 like this way plus ain xn. This is equals bi, I equals 1 to n, and xj greater than equals xj greater than equals 0 for all j equals 1 to n. So, please note that in canonical form we made the inequality as less than equal sign, but whenever I will transform it, I have to make it equality sign. In graphical method, if you remember, we have told that if I have inequality sign, make it equality sign, and then draw the line in two dimensional space. So, here also whether I have less than equal sign or greater than equal sign, by some means I have to convert it into the equality sign. So, and all the constants are equations except this non-negativity constant. Now, suppose I have this one a I1 x1 plus a I2 x2 plus a I n x n, this is less than equals b I. Whenever the equality is less than equals, it is less than equals type of inequality. To make it a equality, I have to add some variable or I have to add some value. So, I can write something like this a I1 x1 plus a I2 x2 plus a I n x n plus say some slack variable x n plus 1, this is equals b I. So, please note that I have added one more value since it was less than equals type, and this x n plus 1 we call it as slack variable. So, basically what happens, we add slack variable in one inequality sign where inequality is less than equals type, or in other sense slack variable is used to make the less than equals type of inequality into the equation type of equation. Similarly, if I have the summation over a I into x1 over I, this is greater than equals b I say. In that case, to make it equality, I have to subtract one variable. So, this I can write down summation over I a1 x1 minus x n plus 1, this is equals b 1, because if I subtract, then this will be equals to b I. So, this variable we are subtracting to make it an equality, and this variable is known as basically the surplus variable. So, if you see, we are using the slack variable we are using the surplus variable to make one inequality type of equation into equality type of equation. So, these are the three type of forms, the matrix forms. From the matrix form, we transform it into the standard form, canonical form. From canonical form, we transform it into the standard form. Then we transform the standard form into the tabular form, and we get the using the initial basic feasible solution and try to improve it and obtain the basic optimum solution. So, in the next class, we will see the theory of the simplex algorithm, that means how one vector is entering, which vector will outgo, and all these things.